Imagine, if you will, standing at the fore of a technological revolution, where machines learn and innovate alongside humans. Picture yourself as the architect behind these intelligent systems, shaping the future of industries from healthcare to finance, from autonomous vehicles to space exploration. No, this isn't science fiction. It's the reality of AI and machine learning, and you're about to embark on a journey to master it. Welcome to the AIML Engineering Advanced Professional Certificate Program. Whether you're just starting your journey into AIML or looking to deepen your expertise, this program is designed to equip you with the skills you need to excel in the world of artificial intelligence and machine learning. In this video, you'll learn what to expect from this program, how the program is structured, and which skills you'll walk away with upon completion of the program. This comprehensive program covers the full spectrum of AI/ML engineering, from foundational concepts all the way to advanced techniques. You'll dive deep into essential areas like supervised and unsupervised learning, deep learning, reinforcement learning, and AI model deployment. But that's not all. We also cover real-world applications, so you'll gain practical skills you can immediately put to use. The program is structured to provide a balance between theory and hands-on experience. You'll not only learn how algorithms work, but you'll also get plenty of opportunities to practice building, training, and deploying models. Each module includes projects and labs that are designed to simulate real-world business challenges, giving you the chance to apply your skills in meaningful ways. AI and machine learning are transforming industries around the world, and the demand for AI/ML engineers is skyrocketing. From healthcare and finance to retail and autonomous systems, AI is reshaping how we work, interact, and make decisions. With this certificate, you'll be well prepared to take advantage of these growing opportunities and become a key player in this evolving, exciting field. By the end of this program, you'll have developed a solid portfolio showcasing your AI/ML expertise. You'll know how to build and deploy machine learning models, fine-tune deep learning networks, and create end-to-end AI solutions that are both scalable and efficient. Whether you're aiming for a role as an AI engineer, data scientist, or ML researcher, this certificate will give you the tools and confidence to take your career to the next level. The future of AI and machine learning is unfolding right now, and you have the opportunity to be at its fore. So here's our challenge to you. Take the initial step of your learning journey by completing the first lesson of this course today. Then commit to regular learning sessions each week. We're excited to have you on board, and we can't wait to see the incredible projects you'll build throughout this journey. Thank you, and welcome again to the AI/ML Engineering Advanced Professional Certificate Program. Imagine being able to predict stock prices, diagnose diseases from medical images, or even teach a computer to play complex games. These aren't just science fiction scenarios, they're real-world applications of AI and machine learning algorithms. In this course, you'll learn the very techniques that make these innovations and others possible. Hi, and welcome. I'm excited to introduce you to the AI/ML Algorithms and Techniques course. Whether you're a newcomer to AI or someone looking to deepen your understanding, this course will guide you through the core algorithms and techniques that power modern artificial intelligence and machine learning applications. This video will help you understand how the course is structured and what skills you'll gain from completing it. Let's look at the skills you'll gain in this course. By the end of the course, you'll be able to implement, evaluate, and explain supervised, unsupervised, and reinforcement learning algorithms. You'll be able to apply feature selection and engineering techniques to improve model performance. You'll be able to describe deep learning models for complex AI tasks, and you'll be able to assess the suitability of various AI/ML techniques for specific business problems. My name is Dr. Mark Damaro. I'm an assistant professor of digital humanities and literature at the University of Pittsburgh Johnstown campus. I was joined in designing this curriculum by my colleagues at Problem Solutions LLC, Dr. Mike Pino, Dr. Dan McCoy, Diane Weaver, and Jimmy Reary. You'll see and hear from some of them as you progress in this course, and in others throughout the program. Each has extensive experience in designing and implementing AI systems. Their insight will help you understand the real-world challenges and opportunities of AI and ML. Now, let's look at the learning journey you'll experience in this course. First, we'll explore a range of machine learning algorithms, from the fundamentals of supervised and unsupervised learning to more advanced topics like deep learning, ensemble methods, and reinforcement learning. You'll learn how these algorithms work, why they're important, and when to apply them to real-world problems. This course isn't just about theory. It's designed to give you plenty of hands-on experience. You'll be working through practical examples and projects where you'll implement algorithms, experiment with different techniques, and fine-tune models. By the end, you'll have the skills to not only understand AI/ML concepts, but also apply them in meaningful, real-world scenarios. We'll cover key areas like regression and classification algorithms. You'll learn how to predict continuous and categorical outcomes using techniques like linear regression, decision trees, and support vector machines. You'll learn about clustering and dimensionality reduction by exploring unsupervised learning methods like K-means and PCA to uncover hidden patterns in data. Then we'll focus on deep learning to understand the basics of neural networks and build models using frameworks like TensorFlow or PyTorch. We'll also look at reinforcement learning and delve into how AI systems learn by trial and error to make their decisions over time. Finally, we'll look at how these algorithms are used in real-world applications across industries. From recommendation systems and fraud detection to image recognition and autonomous systems, you'll see how AI/ML algorithms are solving complex problems each and every day. In this video, you learned how the course is structured and what skills you'll gain. By the end of this course, you'll not only have a solid understanding of key AI/ML algorithms, but also the confidence to implement and optimize these techniques for your own projects. Whether you're looking to advance your career in AI/ML or apply these skills in your current role, this course will give you the foundation you need. I'm thrilled to have you join us on this journey into AI/ML algorithms and techniques. So, here's our challenge to you. Take the initial step of your learning journey by completing the first lesson of this course today. Then, commit to regular learning sessions each week. Imagine you're building an artificial intelligence system to detect fraudulent transactions or navigate a self-driving car safely through city streets. The success of your project hinges on one critical factor: choosing the right algorithm. In your journey with AI, the algorithms you choose can make or break your project's success, whether you're building a self-driving car system or improving fraud detection. In this video, you'll learn how to select and optimize the algorithms that drive high-performing AI solutions, giving you the skills to solve real-world challenges with confidence. By the end of this video, you'll be able to explain the importance of algorithms in AI/ML training and operation. You'll be able to differentiate between supervised, unsupervised, and reinforcement learning algorithms, and identify key factors for selecting appropriate algorithms for specific AI and ML tasks. Let's start with the basics. Why do algorithms matter so much? At its core, an algorithm is a set of instructions that tells a computer how to solve a problem or complete a task. In the context of AI/ML, algorithms define how your model learns patterns from data, makes predictions, or takes actions. The choice of algorithm affects everything, from how efficiently the model processes data to how accurate its ultimate predictions are. For example, If you're working on a classification problem, algorithms like decision trees, support vector machines or SVM, or logistic regression could be your go-to options. A decision tree, for example, might be used when reading a patient MRI and determining which cells might be cancerous versus non-cancerous. For a recommendation system, collaborative filtering or matrix factorization algorithms might be more appropriate. And when it comes to complex tasks like image recognition or natural language processing, deep learning techniques like convolutional neural networks, otherwise known as CNNs, or transformers become indispensable. One of the key skills in artificial intelligence and machine learning is knowing how to choose the right technique for the problem at hand. Each technique has strengths and weaknesses, and understanding these helps you make informed decisions about which approach will deliver the best results. Let's break this down with a few examples. First, supervised learning. If you have labeled data and want to predict outcomes based on past examples, supervised learning algorithms like linear regression or random forests are perfect for tasks such as fraud detection or customer churn prediction. For example, PayPal utilizes machine learning algorithms to analyze transaction data and flag potential fraud based on patterns like unusual spending behavior, location anomalies, or transaction frequency. Next up, unsupervised learning. If your goal is to discover hidden patterns in unlabeled data, unsupervised techniques like k-means clustering or principal component analysis, otherwise known as PCA, are ideal for market segmentation or anomaly detection. Companies like Netflix or Amazon use unsupervised learning algorithms to analyze user preferences, purchasing history, or watching habits to suggest products or content their users are likely to enjoy. Next, reinforcement learning. These are for environments where an agent learns through trial and error to achieve a goal. Reinforcement learning is the way to go in these scenarios. Think of it as the algorithm behind training AI systems for autonomous driving or game-playing bots. For example, self-driving car companies like Waymo or Tesla use these algorithms so the car learns to make decisions based on trial and error, optimizing actions like braking, turning, or accelerating to navigate safely around roads. Another important consideration is the efficiency and scalability of the algorithms you're using. In AIML, not only do you need a model that performs well, but you also need one that scales as your data grows. Think efficiency. Some algorithms are more computationally intensive than others. For instance, deep learning models, while powerful, require significant computational resources, especially when dealing with large data sets or complex tasks. On the other hand, simpler algorithms like k-nearest neighbors, otherwise known as KNN, might be less resource intensive, but may not scale well for massive data sets. Speaking of scalability, as your project or company grows, the volume of data you'll work with will also increase, and the algorithms you choose must be able to handle that growth. For example, decision trees might work well on smaller data sets, but can struggle with larger, more complex data unless optimized. Meanwhile, algorithms like gradient boosting can be highly scalable, especially when paired with modern computing infrastructure like distributed systems or cloud platforms. One of the things you'll quickly learn as an AI/ML practitioner is that your work with algorithms is never static. Here are some key stages you'll experience. Iteration and continuous improvement are key. You'll often start with a simple model and gradually refine it, tweaking algorithms and tuning hyperparameters to enhance performance. Model tuning. This process involves adjusting the settings of your algorithm to get the best results. Techniques like grid search, random search, or even more advanced methods like Bayesian optimization help you find the optimal parameters for your model. Experimentation. Don't be afraid to experiment with different algorithms and techniques. Sometimes the algorithm that seems less suited at first glance can outperform expectations once properly tuned. A willingness to iterate and try new approaches often leads to breakthroughs in model performance. In this video, you've learned the essential concepts of supervised learning, which will help you build more effective machine learning models. You now understand how supervised learning uses labeled data to make predictions, whether through classification or regression, and how key algorithms like linear regression and decision trees operate. You've also gained valuable insight into evaluating model performance using metrics like accuracy and mean squared error, or MSE. Most importantly, you now know how to ensure your model generalizes well to new data, helping you avoid overfitting and build models that perform reliably in all real-world scenarios. Now that you understand the critical role algorithms play in AI/ML, it's time to put your knowledge into practice. Your next challenge: choose a real-world problem you're interested in, like predicting house prices, for example, or detecting fraud or classifying images. Identify 2 to 3 algorithms that might be suitable for that task. You'll then be ready to set up your environment and start implementing impactful solutions. So, let's get to work. Ever wonder how AI systems can predict the next word in your text message or suggest a movie you know you'll love? It's thanks in part to supervised learning. Today, we'll dive into this foundational concept and discover how it shapes many AI applications we rely on every single day. By the end of this video, you'll be able to describe what supervised learning is, how it works, and identify real-world applications of supervised learning. At its core, supervised learning is a type of machine learning where the model learns from labeled data. In this context, labeled means that the data you're already working with has the correct answers or labels assigned to it. The model's job is to learn from this labeled data so that it can make predictions on decisions on new unseen data. For example, imagine you're training a model to distinguish between images of cats and dogs. In a supervised learning scenario, you would provide the model with a set of images that are already labeled as cat or dog. The model would then analyze this data, learn the patterns that differentiate cats from dogs, and eventually be able to correctly label new images as either cat or dog. Let's dive a bit deeper into how supervised learning works. The process typically involves 3 main steps. First, training the model. You start with a data set that contains input-output pairs, where the input is the feature you're interested in, and the output is the correct label or target. For instance, if you're predicting house prices, the input might be the square footage, and the output would be the price of the house. The model learns from these pairs by finding patterns in the data. Second, model prediction. Once the model is trained, it can make predictions on new data that doesn't have a label. For example, if you input a house's square footage into the model, it will predict the house's price based on what it learned during training. Evaluation and adjustment. Finally, after the model makes predictions, it's evaluated for accuracy using a portion of the data that the model hasn't seen before, also known as the test set. Based on the results, you can fine-tune the model to improve its performance. In supervised learning, there are 2 primary types of problems you'll encounter: classification and regression. Classification. This is when the goal is to categorize data into distinct classes or categories. For example, classifying emails as spam or not spam, or identifying whether an image contains a cat or a dog. Here, the model predicts a discrete label. Regression. In regression tasks, the goal is to predict a continuous value. For instance, predicting the price of a house based on its size, or forecasting future sales based on historical data. Unlike classification, regression predicts a numerical value. Understanding the difference between these 2 types of problems is important because the choice of algorithm and evaluation metrics will depend on the type of task you're tackling. Supervised learning offers a wide range of algorithms to choose from, each suited to different types of tasks and data sets. Some of the most commonly used algorithms include linear regression. Used for regression tasks, linear regression predicts a continuous outcome based on the relationship between input variables and the target variable. Logistic regression. Despite its name, logistic regression is a classification algorithm. It's great for binary classification problems, like determining whether an email is spam or not. Decision trees. This algorithm works well for both classification and regression tasks. It builds a tree-like structure where each node represents a decision based on a feature of the data. Support vector machines, or SVMs. SVMs are often used for classification tasks, especially when you have a clear margin of separation between the classes. K-nearest neighbors, or KNN. This is a simple, yet powerful classification algorithm that makes predictions based on the neighbors closest to a given data point. Each of these algorithms has its own strengths and weaknesses, and selecting the right one depends on the specific problem you're trying to solve. So, where do we see supervised learning in action? The answer is pretty much everywhere. Here are just a few examples of how supervised learning is used in the real world. Email spam filters. Supervised learning models analyze incoming emails and predict whether they should be classified as spam or not based on labeled examples. Medical diagnosis. Machine learning models are used to analyze patient data and predict the likelihood of certain diseases based on historical medical records. Fraud detection. In banking and finance, supervised learning helps detect fraudulent transactions by analyzing patterns in transaction data and labeling them as fraudulent or legitimate. Recommendation systems. From Netflix to Amazon, recommendation systems use supervised learning to predict what content or products you'll like based on your past behavior. In conclusion, supervised learning is a cornerstone of modern AI and machine learning. It's incredibly powerful because it allows machines to learn from labeled examples and make accurate predictions on new, unseen data. Whether you're classifying images, predicting prices, or detecting fraud, supervised learning offers the tools you need to tackle a wide range of real-world problems. Now that you know the possibilities of supervised learning, you're ready to discover the key principles and approaches for implementing it. But first, pause for a moment and consider this. Identify 3 everyday interactions you have with technology that might be powered by supervised learning. Keep those in mind as you continue your learning.
Imagine this. You're working for a bank, and your task is to predict which customers are at risk of defaulting on their loans. You have 2 models to choose from, logistic regression and decision trees. But which one will give you the most accurate results? In this video, we'll guide you through implementing and comparing these models in Python to find the answer. By the end of this video, you will be able to implement logistic regression and decision trees, compare and evaluate model performance, and visualize and interpret decision trees. So let's get started. Let's start by creating a new Jupyter notebook. Logistic regression is a classification algorithm commonly used for binary outcomes, where the goal is to predict one of 2 categories. It's simple and interpretable, and often used as a baseline model in machine learning. As you can see, logistic regression implementation in Python is straightforward. We start by importing the necessary libraries, preparing the data, and using train test split to divide our dataset into training and testing sets. Then we initialize the logistic regression model, train it on the data, and use it to make predictions. To evaluate the model, we calculate its accuracy using accuracy_score. Logistic regression is quick to implement and works well for problems where you need simple, interpretable decisions. However, it assumes a linear relationship between the features and the log odds of the outcome, which can be limiting for complex data. Now let's compare this with decision trees. Decision trees are nonlinear models that work by splitting the data into subsets based on feature values. Unlike logistic regression, they can handle more complex relationships between features and the target variable. The implementation of decision trees is similar to that of logistic regression. After importing the decision tree classifier, we initialize the model, train it on the same dataset, and make predictions. Decision trees are flexible and can handle both classification and regression tasks. Like before, we evaluate the decision tree using accuracy. Decision trees tend to perform better on more complex datasets, especially when the relationship between the features and the target variable is nonlinear. However, they are prone to overfitting, especially when the tree becomes too deep. One of the great features of decision trees is their interpretability. We can visualize the tree structure to understand how the model is making decisions. Each node in the tree represents a decision based on a feature value, and the branches show how the data is split. So how do logistic regression and decision trees compare? Logistic regression is simple and interpretable, but it works best with linearly separable data. It's less prone to overfitting, but may struggle with complex patterns in the data. On the other hand, decision trees can model more intricate relationships and are easier to interpret when visualized. However, they are more prone to overfitting if not properly controlled. Both models have their strengths and weaknesses. Logistic regression is great for simple problems with clear linear relationships, while decision trees offer more flexibility for complex nonlinear data. In summary, when choosing between logistic regression and decision trees, it is important to consider the complexity of your data and the problem you're solving. For linear problems, logistic regression is often a good starting point, but if your data has nonlinear patterns, decision trees might give better results. As always, try multiple models and evaluate them based on your specific use case. Now that you've got a solid understanding of logistic regression and decision trees, you're ready to move from theory to practice with actual datasets. Experiment with your own datasets and see which model works best for your problem, or try implementing both models on a public dataset and compare their performance. Imagine building a system that predicts whether a student will pass or fail based on their study hours. How do you know if your model is actually reliable? Sounds simple, right? But what if that system mistakenly tells a hardworking student that they're going to fail, crushing their motivation? Or worse, what if it gives false hope to a student who needs extra help? In this video, we'll walk through key evaluation metrics like accuracy, precision, recall, and more to help you assess your machine learning models effectively. By the end of this video, you will be able to explain how to evaluate the performance of machine learning models using the most important metrics, including accuracy, precision, recall, F1 score, and R-squared. Let's start by opening a new Jupyter notebook. Now, let's load our dataset. We'll be working with a dataset that includes features like study hours and exam scores to predict whether students pass or fail. This is a binary classification problem, so we'll use classification metrics like accuracy, precision, and recall. We'll split the dataset into training and testing sets, then train a logistic regression model to predict whether a student passes or fails based on their study hours and previous exam score. Now that we've trained our model, let's evaluate its performance using accuracy, one of the most common metrics for classification tasks. Accuracy measures the proportion of correct predictions out of all predictions made by the model. In this case, our model achieved an accuracy of 1.0, meaning that it made all predictions correctly on the test data. However, accuracy doesn't always tell the full story, especially for imbalanced datasets. Let's dig deeper by using other metrics. Next, we'll evaluate the model using precision, recall, and F1 score. These metrics provide a better understanding of how well the model handles positive and negative predictions, especially when the dataset is imbalanced. As you can see, the classification report gives us a detailed breakdown for each class. Precision is the proportion of true positives out of all positive predictions. Recall tells us how many actual positives were correctly predicted, and the F1 score provides a balance between precision and recall. A confusion matrix provides an easy way to visualize the model's performance. It shows the counts of true positives, true negatives, false positives, and false negatives. The confusion matrix provides a clear overview of the model's performance. In this case, there are no false positives or false negatives, meaning the model made no classification errors. Now let's switch gears and work with a regression problem. We'll predict a continuous target variable and evaluate the model using regression metrics like R-squared and mean absolute error, or MAE. R-squared tells us how much of the variance in the target variable is explained by the model. In this case, our model achieved an R-squared of 0.99, meaning 99% of the variance is explained by the features. Mean absolute error measures the average difference between predicted and actual values, giving us an error of just 0.04 points. To recap, we've covered how to evaluate your machine learning models using important metrics like accuracy, precision, recall, and F1 score. You now know how to interpret a confusion matrix to gain deeper insights into your model's performance. And for regression models, you've learned how to use R-squared and MAE to assess predictive accuracy. With these tools, you're ready to confidently evaluate your models. Now it's your turn to put these metrics into practice. Take the dataset you've been working with, or pick a new one, and evaluate your models using accuracy, precision, recall, F1 score, and R-squared. Challenge yourself to improve your model's performance on at least 2 of these metrics. Experiment with different algorithms, tweak your models, and see how these metrics change. By diving into these evaluation techniques, you'll not only refine your skills, but also ensure your models are truly making an impact. Imagine you're developing a medical diagnosis model to detect diseases from patient data. A single train test split might suggest your model performs well, but how can you ensure it generalizes to new patients? In this video, we'll explore cross-validation and multiple metrics to give you a more reliable and comprehensive evaluation of your model. By the end of this video, you'll be able to explain how to use cross-validation and evaluate models with multiple metrics. This will give us a more reliable assessment of our model's performance. Let's get started by creating a new Jupyter notebook. Cross-validation is a technique that improves the reliability of our model evaluation by splitting the data into multiple folds. Instead of relying on a single train test split, we train and test the model on different subsets of data. This ensures that our model's performance isn't tied to a specific data split and gives us a more robust estimate of how it will perform on unseen data. In this example, we're using a 5-fold cross-validation to calculate the accuracy of a logistic regression model. This process trains the model on 4 of the 5 folds and tests it on the remaining fold. The mean accuracy across all folds gives us a reliable measure of the model's performance. Now let's expand our evaluation. Instead of just using accuracy, we'll calculate multiple metrics like precision, recall, and F1 score during cross-validation. These metrics give us a deeper understanding of the model's performance, especially for imbalanced datasets. Here, we're using accuracy, precision, recall, and F1 score for each fold during cross-validation. These metrics provide a comprehensive evaluation of the model's ability to classify both positive and negative cases. By averaging the results across the folds, we get a clearer picture of the model's general performance. Cross-validation is equally important in regression problems. Instead of classification metrics like precision and recall, we'll use R-squared and mean absolute error to evaluate the model's performance. For regression tasks, R-squared tells us how well the model explains the variance in the target variable. The higher the R-squared, the better the model fits the data. Cross-validation ensures that this fit generalizes across multiple data splits. Cross-validation is also useful when tuning hyperparameters. For example, decision trees can easily overfit, so we might want to control the depth of the tree. Using cross-validation, we can test different depths and see which one provides the best performance. Here, we use grid search CV to find the optimal tree depth by testing multiple values during cross-validation. This combination of cross-validation and hyperparameter tuning helps us select the best model configuration. Before we finish, let's quickly review what we've covered. Cross-validation ensures your model performs well on new, unseen data by testing it across multiple data splits. Evaluating with multiple metrics, such as accuracy and F1 score, gives you a more complete understanding of your model's performance. Cross-validation is useful for both classification and regression tasks, and it's essential when optimizing models through hyperparameter tuning. Now it's your turn. Use cross-validation to evaluate an existing model or a new project. Explore multiple metrics like precision, recall, F1 score, and R-squared to get a full understanding of your model's performance. If you're up for a challenge, try hyperparameter tuning with cross-validation. The more you practice, the better you'll get at building reliable models. Two predictive models enter the testing phase. One is bogged down with irrelevant features, performs poorly, and misses key insights. The other uses only the most critical features, runs efficiently, and delivers sharp predictions. What made the difference? In this video, we'll explore feature selection techniques like backward elimination, forward selection, and lasso to ensure your model is on the winning side. In this video, you'll learn how to streamline your machine learning models by applying key feature selection techniques including backward elimination, forward selection, and lasso. By the end, you'll be able to identify and remove irrelevant features, improving both the simplicity and accuracy of your models. Ready to enhance your data skills and take your models to the next level? Let's create a new Jupyter notebook. We'll start with backward elimination, a step-by-step process where we begin with all features and gradually remove those that are not statistically significant based on their p-values, a measure of central tendency. Knowledge of this value permits a statistician or model to accept or reject a data point based on the likelihood that it is statistically significant. This method helps in reducing the model's complexity. As you can see, we start by fitting the model with both features, study hours, and previous exam score, or prev exam score. After checking the p-values, we remove the least significant feature, in this case study hours, and refit the model. This leaves us with a simpler, more focused model. Next up is forward selection, where we start with no features and iteratively add those that provide the most improvement to the model's performance. Let's see how it works. In this method, we evaluate each feature one at a time, adding the one that improves the model the most. This method is particularly useful when you want to understand which features have the most predictive power. In this case, prev exam score is likely to be selected due to its strong correlation with the outcome. Finally, let's look at lasso, a powerful regularization technique that automatically selects features by shrinking less important feature coefficients to 0. Lasso balances between keeping important features and reducing model complexity. Here, lasso automatically reduces the coefficient of study hours to 0, removing it from the model. The remaining feature, prev exam score, is kept because it contributes more to the prediction. This way, Lasso selects important features while maintaining model simplicity. To wrap up, remember these key points. Using feature selection techniques like backward elimination, forward selection, and lasso helps you focus on the most important features, improving your model's performance. Streamlining your dataset reduces complexity and prevents overfitting, making your model both efficient and accurate. Ultimately, feature selection is critical for building machine learning models that are not only effective, but also easy to interpret in real-world situations. Your next step is to apply these techniques to a dataset you're currently working with. Start by identifying a dataset with multiple features, then apply each method we've discussed today. Compare the results and see which technique works best for your specific case.
Imagine you're working on a spam detection system. You need your model to accurately classify emails into spam or not spam based on labeled data. This is a classic example of supervised learning, where the model learns to map inputs to specific outcomes, improving its predictions over time. In this video, we'll summarize the core principles of supervised learning, which are essential to building effective machine learning models. By the end of this video, you will be able to explain supervised learning and describe its key algorithms and evaluation metrics. You'll also be able to explain how to ensure models generalize well to unseen data. Supervised learning is a type of machine learning where the model learns from labeled data. This means we provide the algorithm with input-output pairs, allowing it to understand the relationship between the input features and the target outcomes. There are two main types of supervised learning tasks: classification and regression. In classification, the model predicts discrete categories, like identifying whether an email is spam or not. On the other hand, regression predicts continuous values, like forecasting sales or predicting house prices. Supervised learning models learn by minimizing the difference between their predictions and the actual outcomes. This process, known as error minimization, involves optimizing the model's parameters to reduce those prediction errors. Algorithms like linear regression or logistic regression use techniques like gradient descent to adjust their weights and improve accuracy. Some of the key algorithms we've discussed include linear regression for continuous predictions, decision trees, support vector machines, and neural networks for more complex tasks like classification. Support vector machines, or SVMs, are more effective when dealing with high-dimensional data, such as image recognition. An SVM could be used to classify whether an image contains a cat or a dog by finding the optimal boundary between the two categories, even in complex, multi-dimensional data spaces. Neural networks, especially deep learning models, excel in more complex tasks like facial recognition or natural language processing. These models are capable of learning intricate patterns from large data sets, improving their classification performance through multiple layers of computation. To know how well these models perform, we use evaluation metrics. For classification, we use metrics like accuracy, precision, recall, and the F1 score. For regression tasks, we rely on metrics like mean squared error, or MSE, and R squared. One of the challenges we face in supervised learning is making sure that the model generalizes well to unseen data. This means avoiding overfitting, where the model performs great on the training data but fails on new data. To summarize, supervised learning is a machine learning approach where models learn from labeled data to make predictions, either for classification, predicting categories, or regression, predicting continuous values. Key algorithms include linear regression, decision trees, and neural networks, with evaluation metrics like accuracy, precision, recall, and mean squared error. To ensure models generalize well to unseen data, it's crucial to avoid overfitting by balancing model complexity and model accuracy. Now, it's your turn to put supervised learning into action. Take on a simple classification problem like spam detection or a regression task like predicting house prices. Experiment with different algorithms we've discussed and pay close attention to how you can prevent overfitting. Remember, the goal isn't just accuracy on your training data, but creating a model that generalizes well to new, unseen data. Ever wonder how Netflix knows exactly what show you'll love next, even without any direct input from you? It's using a form of machine learning that doesn't rely on labeled data. This is the power of unsupervised learning. In this video, we'll explore how unsupervised learning uncovers hidden patterns in data and the techniques that make it possible. By the end of this video, you'll be able to explain how this unsupervised learning approach is applied in real-world scenarios, from customer segmentation to anomaly detection. Unsupervised learning is a type of machine learning where the algorithm is given input data without corresponding output labels. Instead of predicting specific outcomes, the algorithm tries to find hidden patterns or intrinsic structures within that data. There are two main types of unsupervised learning techniques: clustering and dimensionality reduction. Clustering involves grouping similar data points together. A popular algorithm used here is k-means, where data points are divided into clusters based on how closely they are related. For example, clustering can help companies segment their customers based on behavior patterns. Netflix customers, for example, tend to watch shows that include similar lead actors or have similar themes or can be grouped into similar genres. Clustering these data points, customer preferences for programming, allows a more direct and suitable recommendation system. Another important area is dimensionality reduction, which is about reducing the number of features in a dataset while retaining as much information as possible. A common method for this is principal component analysis, or PCA, which helps simplify datasets by transforming them into fewer dimensions, making them easier to work with. Unsupervised learning has wide-ranging applications. For example, in marketing, clustering can help businesses group customers together by their purchasing behavior. In healthcare, it can help identify patterns in patient data that might not be immediately obvious. And in anomaly detection, unsupervised learning is used to detect outliers, like fraudulent transactions in financial services. To wrap up, unsupervised learning is all about finding hidden patterns in data. Whether it's clustering customers, reducing dimensions in high-dimensional datasets, or detecting anomalies, it's a powerful tool for gaining insight from unlabeled data. Now, it's time to put unsupervised learning into action. Choose a dataset without labeled outcomes, such as customer purchase history or social media engagement data. Apply a clustering technique, like k-means, to identify distinct groups, or use PCA to simplify a complex dataset with many features. As you experiment, pay attention to the insight you gain and how it could inform business decisions or research directions.
Think of your customer data like a scattered puzzle. Each piece represents a different buying pattern, and your challenge is to bring it all together. Clustering algorithms like k-means and dbScan are your key tools to solve this puzzle, helping you uncover valuable insights into your customer groups. In this video, we'll dive into Python to show you how these algorithms work so you can start identifying patterns that drive smarter, data-driven decisions in your business. By the end of this video, you'll understand the key differences between the k-means and dbScan clustering algorithms. You'll also learn how to implement and visualize these techniques in Python, and how to pre-process and normalize your data for effective clustering results. So let's get started. First, let's start by creating a new Jupyter notebook and setting up the environment. For clustering, we need a few key libraries: pandas for handling data, scikit-learn for clustering algorithms, and matplotlib for visualization. Let's import them into our script. I press Shift-Enter to run the cell and proceed to the next one. Next, let's load the dataset. In this example, we are using a simple dataset with two features, annual income and spending score. Here's how we load it into a pandas data frame. We now have a dataset representing customer behavior based on their annual income and spending score. Before we start clustering, it's important to pre-process the data. Clustering algorithms are sensitive to the scale of the features, so we'll normalize the dataset using standard scalar. Now our data is scaled, meaning both features have the same influence on the clustering process. Let's start with the k-means clustering algorithm. K-means divides the data into a predefined number of clusters. We'll begin by setting k equals 3 clusters. After running k-means, we can see that each data point has been assigned a cluster label, indicating which group it belongs to. Now let's visualize k-means clusters with a scatter plot. Each point will be colored based on its assigned cluster. As you can see, k-means has grouped the data points into 3 clusters based on the similarity of their income and spending scores. Now let's move on to dbScan. Unlike k-means, dbScan is a density-based clustering algorithm that can detect outliers. We'll start by setting up EPS equals 0.5 and min samples equals 3. dbScan assigns labels to clusters and identifies any outliers. Data points labeled -1 are considered noise or outliers. Let's visualize the results of dbScan. In this plot, the outliers will be displayed as a different color from the clusters. As you can see, dbScan has grouped the data points into clusters while identifying some outliers shown in a separate color. Let's recap what we covered today. K-means is great for grouping data into predefined clusters, while dbScan is useful for detecting clusters of varying shapes and identifying outliers. Remember, pre-processing your data with scaling is crucial to ensure accurate results with both algorithms. Finally, visualizing your clusters helps uncover hidden patterns and gives you valuable insights into customer behavior. The more you put these techniques into practice, the better you'll become at finding meaningful patterns. This practice will enhance your ability to make data-driven decisions and identify key trends within your data. So now it's your turn to become a clustering expert. Take a dataset from your own work or find an interesting public dataset. Apply both k-means and dbScan to uncover hidden patterns. Can you identify at least 3 distinct customer groups or behaviors? Imagine you're drowning in a sea of data, trying to make sense of thousands of variables. How do you find the signal in all that noise? That's where dimensionality reduction comes in. In the world of data science, the ability to simplify complex datasets is a game changer. Whether you're building machine learning models or conducting exploratory analysis, dimensionality reduction helps you focus on the most important insights. In this video, you'll learn how to use techniques like PCA and TSNE to turn overwhelming data into actionable insights. By the end of this video, you'll be able to simplify high-dimensional datasets using principal component analysis, or PCA, and effectively visualize data patterns with TSNE. We'll also explore how these powerful dimensionality reduction techniques can be applied to real-world data challenges, giving you the skills to uncover hidden insights and improve your analyses. Imagine we have a data set with customer purchase behavior that includes several features like income, spending score, and age. Open a new Jupyter notebook. And we can create this data set. When working with high-dimensional data sets, it can be challenging to build effective models. We'll use dimensionality reduction techniques to reduce the complexity and retain valuable insights. This dataset includes 3 features: annual income, spending score, and age. and we'll apply dimensionality reduction to simplify this data while retaining key patterns. Let's start by normalizing and displaying the data on a 3D scatterplot. First, we'll normalize the data, then we'll convert it to a data frame for easier handling, and then plot it on a 3D scatterplot using matplotlib. Now we'll use principal component analysis. PCA will help us reduce the dimensions from 3 to 2 while retaining most of the variance in the dataset. Here, we import decomposition from scikit-learn, apply PCA to reduce the number of dimensions from 3 to 2, and then convert the data back to a data frame for easier handling. By applying PCA, we've reduced the dataset to two principal components, PCA1 and PCA2. These components capture most of the variance in the original dataset, but with fewer dimensions. Next, let's visualize the two principal components to understand how PCA simplifies the dataset. As you can see, the data is now represented in 2 dimensions. This simplification can help with data analysis, visualization, and modeling. Let's now apply TSNE, or T-distributed stochastic neighbor embedding, a powerful technique for visualizing high-dimensional data. Unlike PCA, TSNE focuses on preserving local similarities, making it great for identifying clusters. First, we'll import manifold from scikit-learn. Then we'll apply TSNE to our data to reduce the number of dimensions to 2. Then we'll convert the data back to a data frame for easier handling. TSNE has compressed the data into 2 components similar to PCA, but with a focus on preserving local structures, which is useful for cluster analysis. Let's visualize the results of TSNE to understand how it identifies clusters and patterns in the dataset. We will do this by plotting the TSNE components using matplotlib. As you can see, TSNE highlights clusters in the data that may not have been as obvious with PCA. This technique is particularly useful for datasets where the cluster structure is important. In this video, we applied PCA and TSNE to reduce the dimensionality of a dataset and visualize the results. While PCA is great for simplifying data while retaining global variance, TSNE excels at preserving local structures and identifying clusters. To wrap up, here are the key takeaways for this lesson. First, PCA helps simplify complex datasets by reducing their dimensions. Second, TSNE is great for uncovering local patterns and clusters. Finally, dimensionality reduction techniques enhance data visualization and make your models more effective. Your next step is to apply these techniques to a dataset you're currently working with. Try using PCA and TSNE to see how they can simplify and reveal patterns in your data. What new insights can you uncover? Through your experimenting, you'll not only gain insights that can drive better decisions, but also make your models more robust and efficient. And the more you practice, the more confident you'll become in using these tools. Imagine you have a massive customer data set, but it's just numbers without any clear story. How do you turn this sea of data into meaningful insights? That's where clustering and dimensionality reduction come in. These techniques will transform raw data into a clear picture of your customer's behavior. In this video, you'll learn 3 key skills. First, you'll discover how to identify and apply unsupervised learning techniques like k-means, dbScan, and PCA to reveal hidden structures in your data. Next, we'll guide you in visualizing and interpreting clustering results specifically for customer segmentation. Finally, you'll understand how to reduce the complexity of a dataset using PCA while keeping the most important information intact. By the end of this video, you'll have the tools you need to make sense of unstructured data and extract meaningful insights. Let's get started. To begin, let's create a new Jupyter notebook. We have a simple dataset with customer features like annual income, spending score, and age. First, we load the data and normalize it using standard scalar to ensure that all features contribute equally to the unsupervised learning algorithms. As you can see, we've scaled the data so that each feature has a mean of 0 and a standard deviation of 1. This processing step is crucial for methods like k-means and PCA. Next, we apply k-means clustering to segment the customers into 3 clusters based on their spending behavior, income, and age. First, we import k-means from scikit-learn's cluster library. Then we apply k-means clustering into 3 distinct clusters, and then we display the first set of that data. K-means has grouped the customers into 3 clusters. Now let's visualize the results to see how these clusters are distributed. We'll visualize the k-means clusters using matplotlib's pyplot library. As you can see, k-means has grouped the customers into 3 distinct clusters based on their income and spending score. Now, let's apply dbscan, a density-based clustering algorithm. dbscan can identify irregularly shaped clusters and detect outliers. Let's see how it compares to k-means for this dataset. First, we'll import dbscan from scikit-learn's cluster section. Then, we'll apply dbscan with custom parameters and display the cluster assignments and outliers. In dbscan, points labeled -1 in the dbscan cluster column are considered outliers. Let's visualize the dbscan results to see how it identifies clusters and outliers. Unlike k-means, dbscan identifies outliers in the dataset and groups customers based on the density of their data points. Now let's apply PCA to reduce the dimensionality of the dataset. We'll project the 3 features down to 2 principal components for easier visualization while retaining the maximum variance in the data. To do this, we'll import PCA from scikit-learn.decomposition. Then we'll apply PCA to reduce the number of dimensions from 3 to 2 and convert the PCA results back to a data frame for easier handling. PCA has reduced the dataset to 2 principal components. Now, let's visualize the results to see how the clusters look after dimensionality reduction. PCA has simplified the dataset into 2 dimensions while retaining most of the data's variance. You can see that the k-means clusters are still well separated, even after reducing the number of features. Let's recap the key takeaways from this video. First, k-means clustering allows us to group data into clusters based on feature similarities. It grouped customers into distinct clusters based on their spending behavior. Next, dbscan excels at identifying irregular clusters and detecting outliers in the dataset. Finally, PCA helps reduce the complexity of our data by transforming it into fewer dimensions while still keeping the most important information intact. Transforming the data into 2 dimensions made it easier to visualize the clusters. Together, these techniques gave you powerful tools for uncovering hidden patterns in your data. Remember, the more you practice, the better you'll become at uncovering hidden insights and making data-driven decisions. So, dive into your data, experiment with these methods, and transform scattered pieces into a clear, meaningful picture.
Imagine training an artificial intelligence the same way you train a dog, with rewards for good behavior, penalties for mistakes. This isn't science fiction. It's the essence of reinforcement learning. In this video, we'll dive into how AI learns to make decisions through trial and error, mastering tasks from self-driving cars to game strategy. By the end of this video, you'll be able to describe what reinforcement learning is and how it's being used in real-world scenarios. Reinforcement learning, or RL, is a type of machine learning where an agent learns by interacting with an environment to achieve a goal. Unlike supervised learning, where the model learns from labeled data, or unsupervised learning, where the model tries to uncover hidden patterns, RL is all about trial and error. In RL, the agent makes decisions, called actions, and receives rewards, or penalties, based on those decisions. Over time, the agent learns to take actions that maximize the total reward. Think of it like training a dog with treats. Good behavior gets rewarded, and bad behavior gets ignored or penalized. Let's break down the key components of reinforcement learning. Agent, the decision maker, like a robot or software program. Environment, the world with which the agent interacts, whether it's a physical space or a simulated world. State, a snapshot of the environment at a given time. Action, the choice the agent can make. Reward, feedback from the environment, positive or negative, that tells the agent how well it's doing. Policy, the strategy the agent uses to decide which actions to take in a given state. The agent's goal is to find a policy that maximizes long-term rewards by learning from its experience with the environment. One of the main challenges in reinforcement learning is finding the right balance between exploration and exploitation. Exploration is when the agent tries new actions to discover their potential rewards. For example, a chess-playing agent which attempts bold new strategies to see if they pay off with a higher reward. Exploitation is when the agent uses what it already knows to get the highest reward. For example, the same chess-playing agent which has a favored opening gambit, for example, which tends to lead to a better long game state in the long run, statistically speaking. The agent needs to explore to learn, but it also needs to exploit the best strategies it has already discovered. The overall goal is to optimize long-term rewards. Reinforcement learning has some fascinating real-world applications. For example, it's used in self-driving cars, where the car learns how to navigate roads safely and efficiently by interacting with its environment. RL helps the vehicle learn to make decisions like when to change lanes, how to navigate intersections, and how to respond to unexpected obstacles, all while prioritizing safety and efficiency. In this circumstance, knowledge of not only traffic laws, but the rules of the road can be beneficial to design. In robotics, RL helps robots learn tasks like walking, picking up objects, or assembling parts. It's also popular in gaming, where AI agents learn how to beat human players or master complex games like chess or Go. So, to sum up, reinforcement learning is all about learning by doing. An agent interacts with its environment, receives feedback, and learns the best way to act over time. It's a powerful approach, especially when problems are the right answer aren't clear from the start, and trial and error is the best way to learn. Imagine how you can use this tool to solve complex, real-world problems. Now that you understand the basics of reinforcement learning, try to identify a problem in your field that could benefit from this approach. Could RL optimize your company's supply chain, improve customer service chatbots, or even help in personal goal setting?
Imagine you're designing an AI that can beat world champions at chess or create a robot that can navigate complex terrains. How do you teach these systems to make decisions? In this video, we are diving into two powerful reinforcement learning techniques, Q-learning and policy gradients, that make these incredible feats possible. By the end of this video, you will be able to understand the basics of Q-learning and policy gradients, implement both algorithms in Python, and know when to use Q-learning or policy gradients. Let's start with Q-learning, a value-based reinforcement learning algorithm. In Q-learning, the agent learns a Q value for each state-action pair, updating its knowledge using the Bellman equation. Let's create a Jupyter notebook. Here's a simple Python implementation. I've copied and pasted this code. It'll be made available to you as a file you can download. We first define the environment, the number of states, and the number of possible actions that the agent can take. Then we define a queue table, initialize it to zeros, and set up the hyperparameters, the learning rate, the discount factor, and the exploration rate. We then define an example learning loop and iterate through it 1,000 times to train the model. In this example, the agent chooses actions using the epsilon greedy strategy, sometimes exploring, sometimes exploiting what it already knows. The Q value for each state action pair is updated based on the Bellman equation, balancing immediate rewards with potential future rewards. Now, let's move on to policy gradient methods. Unlike Q-learning, which focuses on learning Q values, policy gradients directly optimize the policy. The agent learns a mapping from states to actions without needing to estimate value functions. This makes policy gradients particularly useful in continuous or high-dimensional action spaces. Here's an example of a policy gradient implementation using TensorFlow. As usual, we can ignore these CUDA errors. We'll build a simple policy network which outputs probabilities for actions given the current action state. We defined the number of states and the number of actions. We built the policy model, and we built a function to sample an action based on policy distribution. We defined an example learning loop and iterate through it 1,000 times to train the model. In this policy gradient implementation, the agent learns a probability distribution over actions for each state and uses the reinforce algorithm to update the policy parameters based on the cumulative rewards collected during each episode. The model is optimized to increase the probability of actions that lead to higher rewards. Now that we've seen both implementations, let's compare Q-learning and policy gradients in terms of their approach and application. Q-learning uses value-based methods to estimate the Q values of state-action pairs and is effective for discrete action spaces, often employing the epsilon greedy strategy for exploration. In contrast, policy gradient directly learns the policy mapping states to actions, making it suitable for continuous or high-dimensional action spaces, and uses gradient descent to optimize the policy. Q-learning is typically used for simpler environments with discrete actions, while policy gradients are better suited for more complex tasks with continuous actions, such as robotics. For instance, in the classic video games like Pong, where actions are limited to simple moves like left, right, or stay, Q-learning efficiently learns the best action by updating its action value function, its Q function, through rewards obtained from the environment. In contrast, policy gradients are more appropriate for environments with continuous action spaces, such as controlling a robotic arm, where actions involve fine, continuous adjustments like varying joint angles. This approach is advantageous in environments where randomness and exploration are essential for finding optimal solutions. So, when should you use each method? Use Q-learning when the action space is small and discrete. You need a straightforward approach to estimate state action values. The environment is less complex and can be modeled with a Q table. Use policy gradients when the action space is large or continuous. You need a more flexible approach that can handle complex policies. You are working with high-dimensional environments like video games or robotics. Ultimately, the choice between these two models depends on the problem you're trying to solve. For simpler problems with a small number of actions, Q-learning works well. But for more complex tasks, policy gradient methods provide the flexibility you need. We've covered the fundamentals of how Q-learning and policy gradients work, explored examples, and discussed how and when to use each method. Take what you've learned about Q-learning and policy gradients and apply them to different environments. Compare their performance. Which one learns faster? Which one achieves a higher score? Whether you're optimizing decision-making in robotics or creating intelligent game agents, mastering these powerful algorithms will give you the tools to drive impactful AI solutions. Imagine you've built a reinforcement learning agent to play chess. It's making moves, but is it actually improving? How can you tell if it's learning to be a grandmaster or just randomly pushing pieces around the board? How do you know if your reinforcement learning agent is actually learning or just wandering aimlessly? What metrics can you use to track its performance? In this video, we'll explore how to answer these questions with actionable metrics that separate successful RL or reinforcement learning agents from those stuck in an endless loop of trial and error. By the end of this video, you will be able to apply key metrics like cumulative reward and success rate to evaluate reinforcement learning or RL agents, implement and analyze Q-learning agents in Python, and use evaluation metrics to track RL model progress. Let's begin by creating a Jupyter Notebook. I'll be copying and pasting code into this Jupyter Notebook. This code will be made available for you to download. For this demonstration, we'll use a simple grid environment where the agent's task is to navigate to a goal located in the bottom right corner. Along the way, it must avoid pitfalls that incur penalties. As usual, I press Shift-Enter to run the current cell and proceed to the next one. We'll train an agent using Q-learning and evaluate its performance using metrics such as cumulative reward, episode length, and success rate. We'll use the Q-learning algorithm to train our agent. It will explore the environment, collect rewards, and update its policy over multiple episodes. Here's a simple loop where the agent learns from its interactions. First, we define the epsilon greedy action and define the hyperparameters, the learning rate, the discount factor, and the exploration rate for the epsilon greedy policy. Then we'll initialize the Q table and define the training loop. We'll iterate through the training loop 1,000 times to train the agent. Now that our agent is trained, we can start applying evaluation metrics to assess its performance. The first metric we'll look at is cumulative reward, which shows us the total rewards the agent collects during each episode. This metric is key in reinforcement learning because it indicates how well the agent is maximizing the reward system. Here, we see the agent's cumulative rewards are not improving much over time, which means it's not learning fast enough to avoid pitfalls and reach the goal more frequently. More hyperparameter tuning is required. This is what your job as an AI/ML engineer will often look like, trying to train a model and making adjustments when things don't work as you expected. If this were a model for a self-driving car, would you want to ride in it? In self-driving cars, cumulative reward can be used to evaluate how well an RL agent learns to navigate the roads safely. The agent collects rewards for staying in lanes, obeying traffic signals, and avoiding collisions. Over time, increasing cumulative rewards would indicate that the car is learning to drive more effectively. Next, we'll analyze the episode length, which measures the number of steps the agent takes to complete an episode. Shorter episode lengths may indicate that the agent is becoming more efficient at reaching the goal. We'll train the agent over another 1,000 episodes, this time making sure to store the episode lengths. Then, we'll use matplotlib to plot a histogram of episode lengths. As we can see, the episode lengths are mostly very short. If the episode lengths decrease over time, that could indicate it is learning to navigate the environment more effectively. We'll redefine the epsilon greedy action and make a new loop to train our agent. After completing this loop, we'll calculate the success rate and the exploration versus exploitation ratio and print it. The success rate gives us a clear picture of how often the agent is completing the task, and the exploration-exploitation ratio helps us evaluate how well the agent is balancing its actions. The success rate suggests that this model is not yet ready for deployment, and the exploration-exploitation ratio indicates that the model spends most of its time exploiting rather than exploring. Perhaps changing the hyperparameters with the goal of changing this ratio will help the model learn faster and improve its accuracy. In healthcare, success rate can be used to evaluate an RL agent tasked with optimizing treatment plans for patients. The success rate would track how often the agent recommends a treatment that leads to positive outcomes, such as recovery or symptom improvement. In financial trading, the exploration versus exploitation ratio can help evaluate an RL-based trading system. Good balance between exploration, trying new strategies, and exploitation, using known profitable strategies, is crucial for adapting to changing market conditions and making consistently profitable trades. In this video, we explored how to evaluate reinforcement learning agents using key metrics like cumulative reward, episode length, success rate, and exploration-exploitation ratios. We demonstrated a simple Q-learning agent navigating a grid environment, showing how these metrics help assess the agent's performance and learning progress. These metrics are crucial for understanding how effectively your agent is at learning and adapting. By tracking them, you'll gain insights into your model's behavior and be able to make data-driven adjustments for better performance. The implications are significant. Mastering these evaluation techniques can lead to more efficient and effective RL agents, whether you're working on game AI, robotics, or autonomous systems. Now it's your turn to put these evaluation techniques into practice. Take the Q-learning agent we built today and try modifying the reward structure or environment. Use the metrics we discussed to track how these changes impact the agent's performance. By experimenting with different scenarios, you'll gain a deeper understanding of how to optimize RL agents for real-world applications. Remember, the path to building effective AI systems starts with mastering these fundamental evaluation techniques.
Have you ever wondered why machine learning is so versatile? Tackling problems as diverse as predicting house prices, uncovering hidden customer segments, and even training self-driving cars? The secret lies in the different learning paradigms: supervised, unsupervised, and reinforcement learning. In this video, we're going to break down these three powerful approaches, showing you how they work and where they excel. By the end of this video, you'll be able to describe how supervised, unsupervised, and reinforcement learning work, and identify real-world scenarios where each approach excels. First, let's talk about supervised learning. This is probably the most familiar paradigm, where we train a model on a dataset that has both inputs and corresponding labels. For example, if we want to predict house prices, we provide the model with features like square footage, number of bedrooms, and location, along with the actual house prices, of course. The model learns to map the inputs to the correct outputs. Real estate agents and services can utilize this type of supervised learning to predict market trends. Investment companies and contractors can do the same. This approach is great when we have labeled data, and it's widely used in classification and regression tasks like image recognition, spam detection, and price prediction. The key is that the model learns from labeled examples and uses this knowledge to make predictions on new, unseen data. Now, in contrast to supervised learning, we have unsupervised learning. Here, the goal is to find patterns in data without any predefined labels. This is perfect for tasks like customer segmentation, where you want to group customers based on their purchasing behavior, but don't know beforehand how they should be categorized. Perhaps, for example, we want to know if our customers, let's say for shoes, are purchasing on price, reliability, or style. And if style, then which style aspect is of most importance to them. Clustering techniques like k-means are commonly used in unsupervised learning to discover hidden structures in data. It's useful when you don't have labels and just want to explore the underlying patterns. Other techniques include dimensionality reduction and association rules. And finally, we have reinforcement learning, which is quite different from the other two paradigms. In reinforcement learning, an agent learns by interacting with an environment, taking actions and receiving feedback in the form of rewards or penalties. Over time, the agent adjusts its strategy to maximize long-term rewards. This approach is used in scenarios where decision-making happens over time, like training an AI to play chess or teaching a robot to navigate a space. The agent learns through trial and error, constantly updating its understanding of what actions lead to the best outcomes. To sum up, supervised learning works best when you have labeled data and a clear output to predict. Unsupervised learning is ideal for discovering hidden patterns or relationships in your data when you don't have labels. And reinforcement learning is perfect for situations where an agent needs to learn through interaction, adapting its actions based on feedback from the environment. So, as you move forward in your machine learning journey, think carefully about the type of problem you're solving and the data you have available. Each approach, supervised, unsupervised, and reinforcement learning, has its strengths and weaknesses, and choosing the right one will set you up for success. Now it's your turn to put this knowledge into practice. Choose a dataset you're working with, or find an interesting public dataset. Based on what you've learned, decide which learning paradigm would be most appropriate for analyzing this data. Then start implementing your chosen approach. Remember, the best way to truly understand these concepts is to apply them to real-world problems.
Picture this. You're tasked with predicting which homes will sell fastest in a competitive market, segmenting customers for a new marketing campaign, and training an AI to beat a challenging game, all in 1 week. Each of these problems requires a different machine learning approach. How do you decide which method to use? In this video, we'll guide you through each scenario, demonstrating how to apply supervised, unsupervised, and reinforcement learning to tackle these challenges effectively. We're going to review how to predict outcomes using linear regression in supervised learning, segment data with k-means clustering in unsupervised learning, and train AI using Q-learning for reinforcement learning tasks. Let's get started. First, let's tackle the supervised learning task, where we were asked to predict house prices using features like square footage and the number of bedrooms. Let's create a new Jupyter notebook. I will be copying and pasting code into this Jupyter notebook. This code will be made available for you to download. As usual, I press Shift-Enter to run the cell and proceed to the next one. As you can see, we've trained a linear regression model on this example training data. The next step is to evaluate the model's performance using mean squared error, which tells us how far our predictions are from the actual prices. If your model performed well, you should see a reasonably low mean squared error. This means the model is not making accurate predictions based on the training data. It needs more training or more data to train on. Next, let's move on to the unsupervised learning task, where we performed customer segmentation using k-means clustering. We used customer data such as the number of purchases and total spending. The k-means algorithm has grouped customers into 2 clusters. By examining the cluster centers, we can see the characteristics of each group. For example, one cluster might represent higher spending customers, while the other represents lower spending customers. Visualizing the clusters helps us understand how the algorithm grouped the customers. Different colors represent different clusters, making it easier to identify customer segments based on their purchasing behavior. Finally, let's dive into the reinforcement learning task, where we learned to train an AI to play tic-tac-toe using Q-learning. In this case, the agent received rewards for winning and penalties for losing. We start by initializing the queue table and making a tic-tac-toe board. We also define the function that checks to see if the agent or its opponent has won or drawn. We get the list of available actions that the opponent or the agent can take, and then we define the agent's epsilon greedy policy. Then we define the train function for the agent, including all possible game outcomes. Then we train the agent for 10,000 episodes, calculating the moving average of win rate, and then displaying it. The queue learning algorithm updates the queue table based on the agent's actions and rewards. Over time, the agent learns which actions lead to better outcomes, allowing it to improve its gameplay strategy. By the end of the training, the agent should be able to play tic-tac-toe effectively, maximizing its chances of winning by making optimal moves. To sum up, we've successfully implemented and reviewed the three main learning paradigms. In the supervised learning task, we predicted house prices using linear regression. In the unsupervised learning task, we grouped customers using k-means clustering. And in the reinforcement learning task, we trained an AI to play tic-tac-toe using Q-learning. By working through these tasks, you should now have a clearer understanding of when to apply each learning method and how they differ in their approaches to learning. Keep experimenting with these algorithms to further strengthen your machine learning skills. Now it's your turn to apply these learning methods. Start by identifying a problem you want to solve, whether it's classifying data, discovering patterns, or training an agent to make decisions. Use what you've learned to choose the appropriate method, supervised, unsupervised, or reinforcement learning, and implement it. Experiment with different algorithms, evaluate their performance, and see how they fit into real-world applications.
Have you ever wondered how banks decide who gets approved for a loan? How online retailers know exactly what products to recommend? Or how autonomous robots navigate complex environments? The answer lies in the application of machine learning paradigms. In this video, we'll explore how leading companies across various industries are harnessing the power of supervised, unsupervised, and reinforcement learning to solve real-world challenges and transform their operations. Let's dive into the fascinating ways machine learning is shaping the future. By the end of this video, you'll be able to describe how leading companies are leveraging these techniques to solve problems across different sectors. Supervised learning plays a critical role in the financial industry. One key application is in credit scoring. Financial institutions, like banks, use supervised learning models to predict whether a customer is likely to default on a loan. These models are trained on historical data such as income, debt, and credit history to identify patterns that correlate with loan default risk. By using algorithms like logistic regression or random forests, these companies can predict the likelihood of default and make more informed decisions about whether or not to approve loans. These predictions help reduce risk while ensuring that customers with good credit histories get better interest rates. In the world of marketing and retail, unsupervised learning is a game changer. Companies like Amazon and Walmart use clustering techniques to group customers based on purchasing behaviors. These segments help personalize marketing strategies, ensuring that each customer receives the most relevant recommendations. Through algorithms like k-means clustering, businesses can identify high-value customers, understand purchasing trends, and predict which product categories might interest different groups. This leads to targeted promotions that not only boost sales, but also improve customer satisfaction. Let's switch gears to reinforcement learning and its application in robotics. One prominent example is autonomous robots used in industrial settings, like those developed by companies such as Boston Dynamics or Tesla. These robots learn to navigate complex environments, such as factory floors, by receiving feedback on their actions. Reinforcement learning enables these robots to learn through trial and error. As they interact with their surroundings, they receive rewards for successful navigation or task completion. Over time, they refine their movements to become more efficient and avoid obstacles. This capability has revolutionized industries like manufacturing and logistics, where automation is critical, especially for scaling operations. What's truly exciting is how many organizations are combining these paradigms to create robust machine learning solutions. Take Netflix, for example. They use supervised learning to recommend movies based on viewing history, while employing unsupervised learning to identify hidden viewer segments for content development. On top of that, they explore reinforcement learning to optimize content delivery and improve user experience. By leveraging these diverse machine learning techniques, companies can extract more value from their data, making smarter decisions that improve both efficiency and customer experience. To wrap up, we've seen how supervised learning, unsupervised learning, and reinforcement learning are being applied in industries ranging from finance to marketing all the way to robotics. These machine learning paradigms are transforming how businesses operate, helping them solve problems in innovative ways. As you continue learning, think about how these techniques could apply to your own projects, and stay curious about the endless possibilities ahead. Before exploring deep learning and neural networks, take a moment to identify one process in your own work or daily life that could potentially be improved through machine learning. Which paradigm do you think would be most applicable, and why? Ever wondered how your smartphone recognizes your face, or virtual assistants like Siri or Alexa understand your voice commands? The secret lies in neural networks, one of the most powerful concepts in machine learning. In this video, we're going to demystify neural networks, exploring what makes them tick and how they're transforming the world around us. By the end of this video, you'll be able to define neural networks and describe their structure, functionality, and real-world applications. Let's take a closer look at how they work. A neural network is a type of machine learning model that is inspired by the human brain. It consists of interconnected layers of nodes or neurons, which work together to process data and make predictions. At a high level, neural networks are made up of three main components: the input layer, which receives the data, one or more hidden layers, where the learning takes place, and the output layer, where the final prediction is made. Each connection between neurons has a weight that determines the strength of the connection, and this weight is adjusted during training to improve the model's ultimate accuracy. Let's break it down a bit further. Each neuron in the network receives inputs, which are multiplied by their corresponding weights. The weighted sum is then passed through an activation function, a feature that calculates the output of a node within the neural net to introduce nonlinearity, allowing the network to model complex relationships in the data. For example, if we're using the popular ReLU activation function, an activation function which eliminates the problems of vanishing gradients introduced by older functions like sigmoid or ton, the neuron outputs the value if it's positive and 0 otherwise. This process is repeated across all the layers in the network until we reach the final output. One of the most important aspects of neural networks is how they learn. This is done through a process called backpropagation. During training, the network makes predictions, compares them to actual outputs, and calculates an error or loss. The goal is to minimize this loss. Backpropagation works by calculating the gradient of the loss with respect to each weight and adjusting the weights in the direction that minimizes the loss. This is done using an optimization algorithm like gradient descent, which helps the network improve over time. Neural networks are incredibly versatile and are used in a wide range of applications. For instance, they power image recognition systems, allowing your smartphone to detect your face. They also form the backbone of virtual assistants like Siri and Alexa, helping them understand and respond to voice commands. In fields like healthcare, neural networks are used to analyze medical images for diagnosing diseases, and in autonomous driving, they help cars navigate complex environments. The possibilities are truly endless, which is why neural networks are such a critical tool in the AI/ML engineer's toolkit. To wrap up, neural networks are a powerful type of machine learning model inspired by the human brain. They consist of layers of neurons that learn to make predictions by adjusting their weights during training. From image recognition to language processing, neural networks are driving some of the most exciting advancements in artificial intelligence today. Now that you've grasped the fundamentals of neural networks, it's time to put this knowledge into action. Try building a simple neural network model yourself using a framework like TensorFlow or PyTorch. Experiment with different datasets and see how neural networks can be applied to various problems. Understanding how to implement and fine-tune neural networks opens doors to advanced AI applications, from developing innovative tech solutions to enhancing data analysis in various fields.
Fast forward to 6 months from now. You're confidently building neural networks in both TensorFlow and PyTorch, adapting to any project that comes your way. And you landed a job interview for an AI engineer position. The interviewer asks you to explain the differences between TensorFlow and PyTorch in implementing a convolutional neural network, or CNN. How would you respond? In this video, we'll show you how to master both frameworks, setting you up for success in the world of AI. By the end of this video, you'll be able to implement a convolutional neural network using both TensorFlow and PyTorch. You will also be able to compare the key differences in syntax and workflow between the two frameworks and evaluate the performance of models built in each framework. We'll start by creating two Jupyter notebooks named PyTorch Comparison and TensorFlow Comparison. Right-click on the tab, and then click Rename Notebook. If a file called TensorFlow Comparison already exists, click Overwrite. Now, drag PyTorch Comparison to the right side of the screen to view the notebooks side by side. You can only do this in JupyterLab. If you are editing your notebooks on ml.azure.com, you may want to open the PyTorch notebook in a separate window and place your windows side by side. Now, let's load the CIFAR 10 dataset. This dataset contains 60,000 32 by 32 color images across 10 categories. Some of these categories include horses, trucks, dogs, and ships. We use this dataset rather than a set of full resolution images because training on low resolution images is faster and consumes fewer resources. We are using the same dataset for both TensorFlow and PyTorch to ensure a fair comparison. I press Shift-Enter to run the cell and proceed to the next one. Note the error that TensorFlow gives you and the error that PyTorch gives you. These errors can be safely ignored if you are using a virtual machine without a GPU. In TensorFlow, we directly load and normalize the data using train images divided by 255.0, resulting in values for these images between the range of 0 and 1. PyTorch, on the other hand, uses the transforms module to normalize the data to the range -1 to 1, which is the convention in PyTorch. We also define the data loader in PyTorch to handle batching and shuffling. Next, Let's define the architecture of our neural network. We'll implement the same convolutional neural network, or CNN, in both frameworks. Both networks have two convolutional layers followed by pooling, then two fully connected layers. TensorFlow's sequential API simplifies the process by letting you stack layers, while in PyTorch, you explicitly define each layer and handle the forward pass using the forward function. Also, note the errors given here in TensorFlow. Again, these are errors that can be safely ignored if you are using a virtual machine without a GPU. In TensorFlow, we compile the model using the Atom optimizer and a sparse categorical cross-entropy as the loss function. As a reminder, a loss function is a function that measures the difference between a model's output and the desired output. Sparse categorical cross-entropy is one such function that is useful when dealing with many categories of data. PyTorch requires us to explicitly define the optimizer and loss function. As you can see, both frameworks use the Atom optimizer, but the process in PyTorch involves manually defining the criterion, the loss function, and setting up the optimizer. TensorFlow handles this in a more automated way through its compile function. Now, let's train the models. In TensorFlow, we use the fit method to train the model, while in PyTorch, we use a manual loop to handle each epoch and batch. Again, these error messages can be safely ignored. In TensorFlow, the fit function takes care of the entire training process, including batching, loss computation, and backpropagating. In PyTorch, the process is more granular, allowing for more control over each step of the training loop. We'll now jump ahead to the end of the training loops for both PyTorch and TensorFlow. After training, we evaluate the models. TensorFlow again simplifies this with the evaluate method, while PyTorch requires us to manually compute accuracy. In both frameworks, the test accuracy is around 70% for the simple CNN on Scifar 10 after 10 epochs. TensorFlow abstracts away the evaluation process, while PyTorch provides more flexibility but requires manual implementation. In conclusion, both TensorFlow and PyTorch offer powerful tools for building and training neural networks. TensorFlow provides more automation and is often preferred for production environments, while PyTorch offers more control and flexibility, making it popular in research. We've seen that both frameworks achieve similar performance, but the fundamental differences lie in their approach to implementation and debugging. They also have differences in practical use. Say you're running a large website hosted on multiple servers where users upload documents, and you run a model on those documents that summarizes them. You made an update to your model, and now you need to deploy it to all your servers. TensorFlow would be a better choice here for the TensorFlow serving system that it can automatically push your updated model to all your web servers. TensorFlow's orientation towards production environments makes it more rigid, though, and implementing custom layers or loss functions would probably be easier in PyTorch. There are other situations where PyTorch makes more sense. Say you need to create a fine-tuned chatbot to put on your company website. Researchers will often share models on the platform Hugging Face that people can use and modify for free. As of time of recording, Hugging Face has a transformer library with 289 models that work with PyTorch and only 95 that work with TensorFlow. You have better chances to find a better model when you don't limit yourself to models that work with TensorFlow. By gaining expertise in both TensorFlow and PyTorch, you're not just adding tools to your toolbox, you're enhancing your adaptability to tackle diverse AI projects. Whether you're aiming for a career in research or industry, understanding the nuances between these frameworks will set you apart and empower you to choose the right tool for any task. Now it's your turn to put this knowledge into practice. Take a dataset you're familiar with and implement a neural network using both TensorFlow and PyTorch. Pay attention to the differences in syntax, ease of use, and performance. Make note of your findings as you continue to build your expertise in both frameworks. Imagine an AI that can predict tomorrow's stock prices with uncanny accuracy, while another can instantly recognize your friend's face in a crowded photo. How can AI be so versatile? The secret lies in different types of neural networks. Today, we are exploring how feed-forward networks, or FNNs, convolutional neural networks, or CNNs, and recurrent neural networks, or RNNs, each tackle different challenges. By the end of this video, you'll be able to understand use cases for FNNs, CNNs, and RNNs, explain how these neural networks are applied in AI tasks, and identify the best neural network for specific data and problems. Let's dive in. First, let's create a Jupyter notebook. We won't be running any code this time, but it's useful to display it here. Let's talk about feed-forward neural networks, or FNNs. These are the simplest forms of neural networks where information flows in one direction, from the input layer to the output layer, with no loops or feedback. FNNs are ideal for tasks where there's clear mapping between input and output, such as simple regression or classification tasks. For example, let's look at a use case where an FNN is used to predict housing prices. Here's some example code for defining a feed-forward neural network. In this case, the FNN can take up to 10 features, like the number of bedrooms, location, and square footage as input, and predicts the price of a house. Feed-forward networks work well here because the problem is relatively straightforward and there are no sequential dependencies in the data. Next, let's explore convolutional neural networks, or CNNs. CNNs are highly effective for image-related tasks where spatial hierarchies like edges, textures, and objects need to be recognized. One common use case for CNNs is image classification. Imagine you are building a model to recognize handwritten digits from the MNIST dataset. Let's take a look at how a CNN can handle this. Here's some example code for defining a convolutional neural network. Here, the CNN processes the image by passing it through convolutional and pooling layers, which extract features like edges and corners. The flattened features are then passed to fully connected layers for classification. CNNs are the go-to architecture for tasks like image classification, object detection, and even video analysis. The technology is now used in self-driving cars, for example, to recognize road signs and pedestrians, potentially saving lives. Finally, let's look at recurrent neural networks, or RNNs. RNNs are designed to handle sequential data, making them perfect for tasks like time series forecasting, language translation, or sentiment analysis. An excellent use case for RNNs is predicting stock prices based on historical data. Since the order of the data points matters, since a stock's price is affected by its past price, an RNN can capture dependencies over time. Here's some example code for defining a recurrent neural network. In this example, the RNN processes sequences of past stock prices where each input is dependent on the previous inputs. RNNs use their hidden states to maintain the memory of previous data, making them highly suitable for tasks involving sequential or time-dependent data. To recap, feed-forward neural networks are ideal for simple, straightforward tasks like regression and classification. Convolutional neural networks shine when dealing with image data and extracting spatial features. Recurrent neural networks excel at processing sequential data like time series or natural language. Each of these architectures has its strengths, and choosing the right one depends on the type of data and the problem you're solving. Understanding when and how to use each of these architectures is crucial for solving specific problems, from predicting stock prices to recognizing images. By applying FNNs, CNNs, and RNNs appropriately, you can create models that effectively handle tasks like regression, image recognition, and sequence prediction. This knowledge not only makes you more versatile, but also prepares you to adapt to different data types and complexities in real-world projects. Take what you've learned and start experimenting. For your next project, try implementing a simple FNN for a regression task, a CNN for an image classification problem, and an RNN for a time series prediction. Compare their performance and see firsthand how each network type excels in its domain. The skills you gain here are foundational, setting you up for success in more advanced deep learning applications. What if you had the power to predict health outcomes with just a few clicks? Imagine being able to determine a patient's risk of diabetes before symptoms appear. Today, we're going to dive into how you can harness the power of neural networks to do exactly that. Predict whether patients have diabetes using just a few key medical indicators. In this video, we'll guide you step by step through loading a dataset, building a neural network, and evaluating its performance so you can confidently tackle deep learning projects. By the end of this video, you'll be able to load and pre-process a data set for training, build and train a neural network, and evaluate and analyze model performance. First, we'll open a new Jupyter notebook and load the dataset, in this case, the Pima Indians diabetes dataset. This dataset contains several medical predictor variables and a target variable indicating whether a patient has diabetes. As usual, I press Shift-Enter to automatically run the cell and proceed to the next one. Here, we've loaded the dataset from github.com and displayed the first few rows. We can see that the dataset contains several medical attributes, such as glucose levels and BMI, with the target variable, outcome, indicating whether the patient has diabetes, 1, or not, a 0. Before we build our neural network, it's important to pre-process the data. We'll scale the feature values to a range between 0 and 1 using min-max scaler, which ensures that the neural network performs optimally. We've separated the features from the target variable and scaled the features using min-max scaler. Finally, we split the dataset into training and test sets, with 80% of the data used for training and 20% for testing. Now, let's build on our neural network using TensorFlow's Keras API. We'll create a simple feed-forward neural network with 2 hidden layers. We've built a neural network with 64 neurons in the first layer and 32 neurons in the second hidden layer, both using ReLU activation. The output layer uses a sigmoid activation function suitable for binary classification. The model is compiled using the Atom optimizer and binary cross-entropy loss. As usual, you can ignore these error messages if you are using an instance without a GPU. With the model built and compiled, it's time to train it. We'll train the neural network for 50 epochs using a batch size of 32. As we train the model, we can track its performance on both the training and validation sets. This gives us an idea of how well the model is learning and whether it is generalizing properly to unseen data. Once the model has finished training, we'll evaluate its performance on the test data by calculating its accuracy. This tells us how well the model is predicting diabetes for unseen patients. In this case, the model achieved a test accuracy of approximately 75%, which is a solid result. This means the model correctly predicted whether the patient has diabetes around 75% of the time. To gain more insight into how the model performed during training, we'll plot the accuracy and loss over each epoch for both the training and validation sets. These plots give us a visual representation of how well the model learned over time. We can observe whether the model was overfitted or underfitted, whether it found a good balance between the training and validation sets. Now that you've learned how to build and train a neural network to predict health outcomes, it's time to take this knowledge further. You've gained valuable skills in loading and pre-processing datasets, constructing neural networks using TensorFlow, and evaluating model performance. These are crucial steps in applying deep learning to real-world problems, like predicting diabetes in patients. Mastering these techniques empowers you to tackle complex challenges across various domains, from healthcare to finance and beyond. By refining your skills in data preparation, model building, and performance evaluation, you'll be able to develop robust AI models that can provide valuable insights and drive impactful decisions. Now, you can experiment with different datasets, tweak model architectures, and explore advanced techniques to improve your models. The more you practice, the more proficient you'll become in harnessing the power of neural networks to predict and solve real-world problems. Choose a dataset from a field you're interested in and try to build a neural network to predict an outcome with an accuracy of 80% or higher.
Deep learning and neural networks are the driving forces behind today's AI breakthroughs. From diagnosing diseases to powering self-driving cars, these technologies are reshaping entire industries. In this video, we'll explore how they work and how they're applied to solve real-world challenges. By the end of this video, you'll be able to explain how deep learning works, why neural networks are so powerful, and what the future holds for this technology. At its core, deep learning is a subset of machine learning. What makes deep learning unique is that it uses multiple layers of neural networks to automatically learn and extract features from data. The term layers provides a helpful conceptualization of how a deep learning network is organized and how information flows through it. But it does not imply a physical stacking of components. Instead, the connections between neurons and the computations performed within each layer are represented mathematically and implemented through code. These layers, which are called neurons, mimic how the human brain processes information. The more layers we stack, the deeper the network becomes, allowing it to learn from more complex data. Neural networks are particularly powerful because they can take raw data, like images, text, or audio, and automatically learn the patterns and relationships within that data without needing handcrafted features. This is why deep learning has become so popular for tasks like image recognition, speech to text, and even game-playing artificial intelligence. Neural networks have transformed industries by solving problems that were previously impossible or too complex for traditional algorithms. Let's take a few examples. In healthcare, neural networks are being used to analyze medical images, such as X-rays or MRIs, detecting patterns that help doctors diagnose diseases like cancer or heart conditions earlier and more accurately. In fact, deep learning models are now approaching, and in some cases actually surpassing, human-level performance in specific diagnostic tasks. In finance, neural networks are used to detect fraudulent transactions, forecast stock prices, and even automate customer service interactions through chatbots. Their ability to learn from vast amounts of financial data allows companies to make more informed decisions and mitigate risk more efficiently. Two of the most commonly used type of neural networks are convolutional neural networks, CNNs, and recurrent neural networks, RNNs. Let me briefly explain why these are so significant. CNNs are primarily used for analyzing image data. They're able to automatically detect features like edges, textures, and objects within images. This is why CNNs are at the heart of image recognition systems, self-driving car technology, and facial recognition. Every time you unlock your phone using facial recognition, for example, a CNN is working behind the scenes. RNNs, on the other hand, are designed for sequential data, like text or time series. They can remember previous inputs and understand the context of a sequence. This makes them ideal for tasks like language translation, text generation, and time series forecasting. For example, RNNs are used in applications like predictive text and voice assistants to understand the flow of a conversation and provide more accurate responses. One of the most exciting advancements in recent years has been the application of neural networks to generative artificial intelligence, or Gen AI. Models like generative adversarial networks, GANs or GANs, and autoencoders are capable of generating new data from scratch, whether that's creating realistic images, synthesizing music, or writing text. GANs consist of two networks: a generator that creates data, and a discriminator that evaluates it. Through this adversarial process, GANs are able to generate data that looks incredibly realistic, from photorealistic images to, unfortunately, deepfakes. This technology has practical applications in content creation, game development, and even fashion design. Looking forward, the potential for deep learning and neural networks is immense. We're seeing rapid progress in the development of more efficient and scalable neural network architectures, like transformers and self-supervised learning models. These advancements are making it easier to train AI models on larger datasets and solve more complex problems. In the near future, we can expect neural networks to continue pushing boundaries in fields like personalized medicine, autonomous vehicles, climate modeling, and even creative arts. Imagine AI systems that can design new pharmaceuticals, predict natural disasters, or assist in creating personalized art pieces, all powered by the underlying strength of neural networks. In conclusion, deep learning and neural networks are driving some of the most groundbreaking advancements in artificial intelligence today. Their ability to learn from and generate new data is changing industries and unlocking possibilities we never thought possible. As we move forward, the role of neural networks will only grow, shaping the future of technology and innovation. Now that you understand the power of deep learning and neural networks, it's time to put this knowledge into action. Your next step is to choose a real-world problem in your field that could benefit from these technologies. Whether it's improving customer service with chatbots or optimizing supply chain management with predictive analytics, identify a challenge and start exploring how neural networks could provide a solution. Remember, the future of AI is in your hands. What will you create? Have you ever struggled with getting your machine learning projects beyond development? What separates successful AI projects from those that never make it out of development? The secret to success lies in mastering the full AIML engineering workflow. In this video, you'll gain the skills to confidently manage the entire process, from selecting the right model to deploying and monitoring it in the real world. You'll also explore emerging trends that will enhance your ability to build scalable, impactful AI solutions. By the end of this video, you'll be able to explain the full AI/ML engineering workflow, evaluate appropriate model architectures for different data types, and explore emerging trends like AutoML and ML Ops to enhance model development and deployment. At the heart of AI/ML engineering is a systematic workflow. Most AI/ML projects follow a similar process, starting with data collection and moving through stages like data pre-processing, model development, training, evaluation, and finally, deployment. First, data is collected from various sources, such as databases, sensors, or user inputs. After collecting the data, the next crucial step is pre-processing, where we clean, transform, and prepare the data for model development. This involves handling missing data, scaling features, and sometimes creating new features. Next, we move into model development. In this step, engineers choose an appropriate model architecture based on the problem at hand. For instance, if we're working with images, we might select a convolutional neural network, or CNN, while for time series data, we'd likely go for a recurrent neural network, RNN, or long short-term memory, LSTM. Once the model is selected, the training phase begins. Here, the model is fed processed data and iteratively learns patterns by adjusting its weights. Engineers often use optimization techniques like gradient descent and backpropagation to fine-tune the model parameters. After the training phase, it's critical to evaluate the model's performance. This is where we assess how well the model has learned by using a test set, data that the model hasn't seen during training. We measure performance using metrics such as accuracy, precision, recall, or F1 score for classification tasks, and mean squared error, or MSE, or R squared for regression tasks. The goal is to ensure the model generalizes well to unseen data and isn't overfitting to the training set. Once the model has been trained and evaluated, the next step is deployment. This involves integrating the model into a real-world application, such as a web service, a mobile app, or an automated system. Engineers often use platforms like AWS, Microsoft Azure, or Google Cloud AI to deploy models at scale. Deployment doesn't stop at launching the model, however. Ongoing monitoring is essential to ensure the model continues to perform as expected. Models can degrade over time due to changes in the underlying data, a phenomenon known as data drift, so continuous monitoring and retraining are often required. Let's now talk about some of the emerging trends in AI/ML engineering. One of the key advancements is the rise of AutoML, which automates much of the model selection and training process. AutoML tools can help engineers find the best model architecture and hyperparameters faster, reducing development time. Another growing trend is the use of ML Ops, a set of best practices that combine machine learning development with operational practices. ML Ops ensures a seamless collaboration between data scientists, engineers, and operations teams, making it easier to deploy and manage models at scale. By watching this video, you've gained valuable skills in managing the entire AI/ML engineering workflow, ensuring your machine learning projects go beyond development and succeed in production. You now understand the importance of each phase, from data collection and pre-processing to model development, training, and evaluation, along with selecting the right model architectures for different data types. You've also learned the critical role of deployment, monitoring, and retraining models to keep them performing well over time. Additionally, you've explored emerging trends like AutoML, which speeds up model selection, and ML Ops, which streamlines collaboration between teams for smoother deployments. With these insights, you're now equipped to build scalable AI systems that not only make it to production, but also deliver lasting value. Start by mapping out the workflow for your current or next AI project. Identify which stages you're most comfortable with and which might need more attention. Remember, mastering this process is key to moving your projects from development to successful real-world deployment.
Aligning AI with organizational readiness, goals, and ultimately strategically where we want to end up in terms of use cases and what we go after is an incredibly important tool, skill, behavior, everything above that we all need to understand if we're going to be operating in this AI space or in the Azure space as an engineer, ultimately as a strategist. So in one particular example, I had a client who came to us who is very eager to jump right into AI. And what they wanted was predictive models, automation tools. They wanted all of the above, right? Ways to automate their back office, ways to think about workforce automation, and think about kind of the future of work. So their goal, in short, was to modernize a lot of their operations. And they were just, again, incredibly excited to get started. On the surface, it sounded like a great opportunity for us to dive right in. But as we started having conversations with their team, it became incredibly clear that they hadn't defined what they actually wanted to achieve. Some questions we asked were, what problems were they trying to solve? What outcomes were they hoping for? And perhaps most importantly, was their organization even ready for AI? One of the most important, or one of the first things we noticed was their data quality, or rather the lack of it. The data was inconsistent, poorly organized, and frankly, not in a shape to support meaningful AI insights. If we had jumped straight into the building, the tools would have worked as intended. And on top of that, they didn't have clear success metrics. So even if the tools had worked, it wasn't clear how they would measure value. And for us, that was important because we knew that we needed to pause and refocus the effort. So for example, if we looked at a lot of their data architecture and their tech stack, we noticed that for something such as learning and development, they had 7 different applications or sources of truth. So that would present itself as a challenge when we're trying to create a unified experience, but we have to wrangle data in a bevy of different ways, and they didn't have a data lake and an ADL, for example, to go about kind of solving that problem. So instead of building tools right away, we worked with them to prepare for AI. First, we made sure to run workshops with their team to identify their critical challenges and pain points from a business perspective. Then we followed through with the technical feasibility, ideation sessions, and moving forward from that. Then we prioritized improving their data quality. So we wanted, again, to create a solid foundation for any future AI efforts. Finally, we wanted to help them define success metrics and map out high impact use cases, ensuring that their AI tools would align with their business goals when they were ready to move forward. What that in practicality looked like for us was that we would go through an entire ideation session post understanding what their business goals were, in terms of, okay, so these are your goals. How can AI be leveraged in these particular use case opportunities? How do we go about defining what use cases were current AI tools that perhaps they had sitting on the shelf? So think of like a Copilot or perhaps like a Chat GPT. And then what would ultimately be custom solutions. And we wanted to make sure that there was a methodology or a governing principle or framework by the way in which we went about measuring that. So the lesson here in short is you can't just build AI for the sake of it. Jumping in prematurely not only risks failure as a business, but wastes time and resources. What we recognize is AI only works when the organization is ready, when there's clear data, clear goals, and ultimately this alignment with real business needs that are practical. So AI should look to solve problems, not create more.
Imagine this. You're working on an artificial intelligence project with the potential to revolutionize an industry. But despite having cutting-edge algorithms and powerful models, the project stalls. Why? Because the secret to success in AI/ML isn't just in the code, it's in the collaboration. What if you could break down barriers between engineers, data scientists, and business leaders to unlock the full potential of your AI solutions? In this video, we're revealing how mastering collaboration can elevate your career and drive your projects to new heights. Let's dive in and discover how teamwork can turn complex problems into groundbreaking innovations. By the end of this video, you'll be able to explain why collaboration is such an important part of AI/ML professions. In AI/ML projects, collaboration extends beyond your immediate technical team. You'll need to work closely with people from other departments like marketing, operations, or product development who provide valuable insight into the models you're building will be used in real-life scenarios. This interdisciplinary collaboration ensures that your AI solutions are not only technically sound, but also aligned with the business's needs. Effective collaboration leads to innovation. When team members are encouraged to share their expertise and ideas, you open the door to new approaches and solutions. It also helps you identify potential pitfalls early in the process, speeding up problem solving and improving project outcomes. Collaboration fosters a culture of continuous learning, where feedback and diverse perspectives help refine models and processes. Good communication is key to successful collaboration. As an AI/ML professional, it's important not only to be able to explain complex concepts to non-technical stakeholders, but also to listen and understand the challenges from their perspective. Tools like shared notebooks, regular check-ins, and clear documentation make it easier for teams to stay aligned and work toward common business goals. You've gained valuable insight into how collaboration is key to success in AI/ML projects, allowing you to leverage the strengths of data scientists, software developers, and business stakeholders to solve more complex problems more efficiently. Understanding the importance of clear communication and teamwork will help you streamline project timelines, improve decision-making, and ensure your solutions meet real-world business needs. By mastering effective teamwork and communication, you're not just improving project outcomes, you're positioning yourself as an invaluable asset in any AI/ML team. Start applying these collaboration techniques in your current projects. Engage more deeply with your team. Actively seek diverse perspectives and communicate your technical insights clearly. By doing so, you'll not only drive your projects to success, but also elevate your career, making you a more effective and sought-after AI/ML professional. Embrace collaboration and watch how it transforms your work and your impact in the field.
So this is a really interesting one because when talking about the level of conflict that can occur when setting priorities across both technical and business sides of the house, these are often two very different teams with very different kinds of personalities. They also have different drivers and motivators, and sometimes what might come across as conflicting goals for the company. But I want to reassure you that conflict that arises when setting priorities for a roadmap or for a sprint, the conflict that arises can be really beneficial and healthy. Where it can go sideways is when that conflict results in personal harm or damage to the relationships within the team or across the team within the company. There's also something that I want to caution here where it could come to a point where a customer might become aware of an internal conflict, and that can really damage the relationship with the customer. It can damage their confidence in the company's ability to create and deploy a quality product. So it's important. Two things are really important to keep in mind here. One is that we don't air our dirty laundry. When we talk externally with our customers and prospects, we are one team. We are united, no matter how divided we might feel like on the inside. And another thing to really keep in mind here is that as the conflict arises, try your best to not take it personally. Try your best to create a boundary between you emotionally and the discussion at hand. And try to take a step back and look at the priorities from a higher level. Oftentimes, when we disagree on specific priorities, it's because we're so in the weeds with those priorities that we're not seeing the bigger picture or the bigger why. And understanding that bigger why is really key to resolving the conflict, even healthy conflict, right? So keep in mind, this is professional. It's about the work. It's about understanding the work. And ultimately, it's about doing the right thing for the customers and taking care of yourself and taking care of each other on the team and your well-being as you pursue these passionate discussions. Passion is good. So there's kind of two areas that I like to dig in when trying to figure out that bigger picture why. Because the bigger picture why is really how we can unite and gain consensus across a cross-functional team. So one is about deadline-driven priorities, and one is about customer-driven priorities. So deadline-driven priorities and customer-driven priorities, because every gain in either case comes with a trade-off, and that's something really important to keep in mind. So when a priority is set because of a deadline, I like to ask, why is this the deadline and not another date? What are the consequences of the deadline if it shifts? What are the consequences of the deadline if it remains in place? And the exploration around the discussion, the results, when you go into this what if type of scenario, it helps to clarify for all parties what is the true urgency and is there flexibility in the timeline, and if yes, why, and if not, why. On the customer-driven priorities, if a priority is driven by a specific customer request, I like to delve deeper into it by asking, why does the customer want it? What behaviors or trigger events occur before, during, and after this request? That really gets us to uncovering, is this really what they're asking for? Because this happens so often, actually. We'll receive customer requests that are very specific. I want this button over here. Well, what are they actually trying to do, right? So if we can, number one, gather that data, maybe interview that customer and figure out what are they trying to do with that, and then facilitate a discussion about, well, is it even the button that needs to move, or do we actually need to adjust the step that happens before they even reach the button in that sequence? So it just really shifts the conversation. And that's a key thing here. Because there's a natural duality between the front side of the house, the business side, the back side of the house, the technical development team side, there's a natural duality that emerges here. And one of the key things is for folks on both sides to be able to shift their perspective and see the problem from multiple perspectives in order to arrive at a solution that can appease most people, most importantly, the market demand.
You've covered a lot of ground in AI ML engineering, mastering data preprocessing, model development, and deployment. But how do all these pieces fit together to create powerful, real-world solutions? In this video, we'll bring everything into focus, summarizing how each step in the machine learning lifecycle contributes to building, deploying, and maintaining models that truly make a difference. Let's recap and ensure you're ready to take these skills into the real world. By the end of this video, you'll be able to describe the AI ML workflow from data prep to deployment, identify techniques for model evaluation and prevent overfitting, and explain how AI ML models are used in real-world applications. First, let's review the role of the AI ML engineer. AI ML engineers are responsible for designing, building, and deploying machine learning models. This role covers a broad range of tasks, from gathering and pre-processing data to developing models, evaluating performance, and integrating them into production systems. It starts with data collection and pre-processing. One of the foundational tasks for AI ML engineers is working with data. This includes collecting data from various sources, cleaning it up, and transforming it into a format that machine learning models can process effectively. Without well-prepared data, even the most sophisticated models won't perform well. Next, we focused on model development, the heart of AI ML engineering. In this stage, engineers build models that learn patterns in data to make predictions, classify information, or identify trends. Choosing the right model is next. Selecting the right model architecture, whether it's a decision tree, support vector machine, or a deep neural network, depends on both the problem at hand and the type of data available. Engineers experiment with different algorithms and tweak them to achieve the best possible performance. Hyperparameter tuning and experimentation. We also discussed the importance of tuning hyperparameters, such as learning rates and batch sizes, to fine-tune model performance. Model development is iterative, involving multiple experiments to find the optimal balance between accuracy and efficiency. Once a model is developed, it's essential to evaluate its performance. This is where model evaluation comes into play. AI ML engineers use metrics like accuracy, precision, recall, and F1 score to assess classification models. For regression tasks, metrics like mean squared error, or MSE, or R squared are used. You'll also want to avoid overfitting. A key challenge in model evaluation is ensuring that the model generalizes well to unseen data. Overfitting happens when a model performs well on training data, but fails to generalize to new examples. Techniques like cross-validation help mitigate this issue by evaluating the model on multiple data sets. After the model is validated, the next big step is model deployment. AI ML engineers must deploy models into production environments where they interact with real-time data and provide predictions in live applications. Deployment platforms. Many teams use cloud platforms like AWS, Microsoft Azure, or Google Cloud AI to deploy models at scale. Engineers work with developers to integrate the model into applications via APIs or other services. Monitoring and maintenance. Model deployment doesn't end once the system is live. Engineers continuously monitor model performance, watch for issues like model drift, and retrain models as needed to maintain accuracy over time. Of course, collaboration is essential for success in AI ML engineering, as it helps ensure technical solutions align with real-world requirements. We also touched on how AI ML engineering plays out across different industries. In healthcare, for example, engineers develop models to predict patient outcomes or analyze medical images. In finance, AI/ML is used for fraud detection, while in retail, machine learning powers recommendation systems that personalize the shopping experience. Real-world impact. Regardless of the industry, AI/ML engineers need to balance technical model development with practical deployment concerns. The ultimate goal is to build models that not only perform well, but also solve the real-world problem efficiently. We've covered a lot of ground, from data pre-processing and model development to evaluation, deployment, and real-world application. AI/ML engineering requires both deep technical expertise and practical skills in deploying models that work in production environments. Now, it's time to take this knowledge and apply it. By mastering the entire machine learning lifecycle, you're not just building models, you're developing solutions that can transform industries and drive meaningful outcomes. Start applying these techniques to your projects, whether it's in healthcare, finance, or any other field where AI/ML can make a difference. So dive in, experiment, and let your work make an impact. Picture this. Your artificial intelligence model is live, accurately predicting outcomes and adapting to new data in real time. Sounds exciting, right? Well, that's the reality you've been building toward. In this video, we'll recap how you transformed raw data into actionable models, fine-tuned their performance, and deployed them into real-world applications. Let's take a look at the essential skills you've mastered and how they're setting you up for success in AI/ML. By the end of this video, you'll be able to summarize the key components of the AI/ML engineering process, including data pre-processing, model selection, evaluation, deployment, and monitoring, and reflect on the essential skills you've developed throughout the module and their relevance to real-world AI/ML applications. Throughout this module, you've explored foundational concepts of AI/ML engineering. You started with the basics of data collection and pre-processing, where you focused on transforming raw data into something usable for models. You learned about selecting the right algorithms for different tasks, from classification and regression to more complex models like neural networks. You also dove deep into model evaluation, understanding metrics like accuracy, precision, recall, and F1 score. These metrics help ensure that your models are not only performing well in training, but are also generalizing to real-world data. Finally, you explored deployment strategies and the importance of monitoring models in production. Deploying a model is just the beginning. Monitoring its performance and ensuring it adapts to changing data is what keeps your solution robust and useful. In summary, you've learned about essential AI/ML skills like data pre-processing, model evaluation, and deployment strategies. You've come to understand the importance of monitoring and adapting models in real-world scenarios, and you've applied your skills in various ways. I want to take a moment here to thank you for your hard work and dedication throughout this module. AI/ML can be a challenging field, but you've shown great perseverance in tackling the concepts and building your skills. Every hands-on activity, every quiz, and every project you completed has brought you one step closer to mastering these essential tools in AI/ML development. With these skills, from data pre-processing to model deployment and monitoring, you're now prepared to tackle real-world AI/ML challenges across industries, whether it's optimizing supply chains, personalizing user experiences, or revolutionizing healthcare diagnostics. So, are you ready for the next challenge? It's time to put it all together in a complete AI/ML solution for a retail business problem. By the end, you'll solidify your mastery of the machine learning lifecycle. Let's get started. Fast forward a year from now. You're leading AI ML initiatives, solving complex problems, and making significant contributions to your industry. I just want to take a moment and say a huge congratulations to you for completing this course and making that imagined future possible. It's been an incredible journey, and I know you've put in a lot of hard work. From learning the basics of AI ML to tackling real-world problems and building comprehensive solutions, you've truly expanded your skill set. You've gained hands-on experience with supervised and unsupervised learning, built models for different business challenges, and even explored reinforcement learning. These are advanced concepts, and completing this course means you're now equipped to take on AI ML projects in the real world. This is truly just the beginning. AI ML is an ever-evolving field, and I encourage you to keep pushing forward. Continue experimenting, keep refining your skills, and don't be afraid to take on new challenges. You now have the foundation you need to excel in this exciting industry. Once again, congratulations on all your hard work, and thank you for being part of this journey. I wish you all the best in your future AI ML endeavors. Keep up the great work, and good luck.